Today, we're going to dive into what is basically a high-tech recipe. We're on the hunt for a microscopic formula that could have a massive impact on our planet and our technology. So yeah, let's get cooking.
All right, let's kick things off with a bit of a puzzle. What do gaslighters, sonar, and electric guitars all have in common? I know, they seem totally unrelated, right? But believe it or not, they all depend on the exact same and kind of weird physical property.
And that property, it's called piezoelectricity. Putting it simply, it just means pressure equals power. If you squeeze one of these materials, it generates an electric charge. But here's the real magic. It works both ways. If you apply electricity to it, the material actually moves, it vibrates. And it's this two-way street, this conversion of energy back and forth, that makes it so incredibly useful.
Okay, but this is where our story hits a major roadblock. See, the material we've been relying on for this little magic trick for over 50 years, well, it has a really serious, toxic problem.
For decades, the undisputed champion of the piezoelectric world has been this material called PZT. And for good reason. It's super effective, it's reliable, and it became the gold standard for pretty much everything, from medical ultrasounds to all kinds of advanced sensors. But here's the dirty little secret. That P in PZT, it stands for plumbum. That's just the Latin word for lead. And well, we all know lead is bad news. It's a toxic heavy metal, terrible for the environment and for our health. So what that means is that the workhorse of modern electronics basically has a ticking environmental time bomb built right in. We desperately need a better option.
So, this has kicked off a global race among scientists, right? Everyone's trying to find a worthy, lead-free replacement. And that brings us to a really promising contender.
So in one corner, you've got the toxic champ, PZT, and in the other corner, you have this lead-free challenger called BNKT. Now, BNKT is great. It's eco-friendly, it shows a ton of promise, but there's a catch. It just doesn't pack the same piezoelectric punch as its lead-based rival. Not yet, anyway.
So what's really holding BNKT back? Well, it boils down to a few key issues. First, it's a pain to make. It needs really high temperatures. Second, its performance just isn't quite there yet compared to PZT. And finally, its internal structure can be a little unstable. If you want to replace the king, you got to solve these problems.
And this is where the scientists in the paper we're looking at got really clever. They thought, okay, instead of starting all over from scratch, what if we just tweaked the recipe? What if we tried to fix BNKT's flaws by adding a little something extra, a secret ingredient?
So in the world of material science, this is actually a technique called doping. And it's exactly like adding a pinch of a special spice to a recipe to completely change the final dish. In this case, that spice was the element niobium. The scientists added these tiny, super precise amounts of it into the BNKT mixture, crossing their fingers that it would be the key to unlocking its true potential. Now, what's really fascinating is where this secret ingredient actually goes. You're looking at BNK's fundamental atomic structure. It's called a perovskite lattice. Just think of it like a set of atomic Legos clicked together in a really specific repeating pattern. The whole idea is that these tiny niobium atoms are meant to slot right into that pattern, basically swapping places with some of the original atoms and, if all goes well, improving the whole thing from the inside out. And let me tell you, making this stuff is basically an extreme, high-tech baking session. First, you have to weigh all the chemical powders with incredible precision. Then you mix them in what's called a ball mill for a full 24 hours to get everything perfectly uniform. From there, it's a cycle of baking at insane temperatures, crushing it under immense pressure, and then, you guessed it, more baking at over 1,000 degrees Celsius. All of that just to create these final, dense little ceramic pucks that they can actually test.
All right, so the scientists have cooked up several different batches, each one with a slightly different amount of niobium. Now comes the moment of truth. The big question, did the secret ingredient actually work? It was time to find out. So the first thing they did was use X-rays to basically peer deep inside the material's atomic structure. And right away, they saw something. See these peaks on the graph? As they add more niobium, you can actually watch the peaks shift. That's a huge deal. It's telling us that the fundamental shape of the crystal is changing. It's going from a slightly tilted or rhombohedral shape to a much more perfect, uniform cube shape. Okay, so that's what's happening at the tiny atomic level. But what if we zoom out just a little bit? Well, under a powerful electron microscope, this is what the scientists saw. Each of these funky-looking blocks is a crystal grain. And it's pretty obvious, right?
The images clearly show that adding niobium makes these grains grow bigger and way more uniform.
And we can actually put some hard numbers to that. The data shows the grain size gets bigger and bigger as you add niobium, hitting its peak size at about 3%. But here's where it gets interesting, a little twist. When they pushed it further and added 4%, the grains actually started to shrink again. This is our first big clue that there's a sweet spot for this recipe.
Look, bigger grains and a new crystal structure, that's all very interesting, but it's totally meaningless if the material doesn't actually work better. So that brings us to the million-dollar question. Did adding niobium actually improve its performance? Did it boost its piezoelectric power?
And here's the answer. This graph is the big one. It's plotting the electrical performance against how much niobium they added. And just, wow, look at that. The performance absolutely skyrockets, hitting a super clear peak right at 3% niobium. And get this, that's the exact same spot where the grain size was the biggest. But after that peak, performance just falls off a cliff. They found it. They found the recipe's sweet spot.
So the big question is, why? Why does this happen? Well, the data pointed to another huge benefit. It turns out niobium acts like a kind of structural patch. It reduces the number of these tiny atomic defects called oxygen vacancies. The best way to think about them is like microscopic potholes in the material's structure. And these potholes cause energy to just leak out. Niobium comes in and patches those holes, making the whole thing a much, much better insulator. So after all that mixing, all that baking, and all that testing, what's the takeaway? Well, it looks like the scientists really did find a very, very promising recipe for the future of these materials. Okay, so the final verdict is in. Adding a little niobium to BNKT, it absolutely works. It completely changes the material structure right from the atomic level and patches up those defects, making it a way better insulator. But, and this is the key, it's all about moderation. It's not about just dumping in as much as you can. It's about hitting that perfect magic number, right around 3% niobium.
And this is why all of this really matters. I mean, this isn't just some abstract science experiment. This kind of detailed, careful research is a massive step forward. It gets us that much closer to a world where our most advanced electronics, we're talking everything from life-saving medical devices to green energy tech, can be built with materials that are not just powerful, but also safe for us and for the planet.
You know, when you think about it, this entire breakthrough really came down to just adding a tiny pinch of the right element to the recipe. It really makes you wonder, doesn't it? How many other technologies out there could be just one secret ingredient away from being completely, totally transformed?